I thank you for joining me for a Superspace video in which I'm going to make some personal reflections on superspace theory and my process in developing the theory and some of my thoughts about its effects on physics, both in general and with the core principle of a fourth dimension being the direction of small. Now, this video will be best for those who are familiar with superspace theory from my book or other videos, and it will also be a bit more rambling and conversational because that's the point. These are just more personal reflections. And finally, I am recording this outside, so there will be noise such as cars driving by, people talking or shouting, and considering I'm in Eureka, California, possibly screaming. But be that as it may, um, those of you who know at least a little bit about superspace theory know that one of the core, let's pull up something to draw on here. One of the core central principles is that size equals distance at fundamentally smaller levels of physics. And that means that when we move inward to the realms of the very small or the subatomic realms, things are actually no longer getting smaller at all. Instead, they are moving further, they are moving more distant in a fourth dimension, or rather a fourth fundamental direction outside of the 3D, the three-dimensional space of our universe, the three familiar degrees of freedom of our universe. So what we think of as the very small is a fourth fundamental direction, and we won't go into that too much because I cover that in all my videos, I think. But if you create a two-dimensional analogy of our universe and say our 3D space is this 2D field, and so if you have an object here, you have two essential degrees of freedom, but again, this is analogous of our 3D universe. Then when we get to the realms of the very small, we are not getting smaller any longer. When we go into the subatomic realms, we are curving in a fundamentally different direction. That is the fourth dimensional direction. That leads into deeper fields of space where fundamental forces and particles are located. This is part of a greater multidimensional block universe, and it moves from the most energetic fields to the most entropic. So in my book, I go into how, in order to understand all of the phenomenon of our universe, we have to understand that underlying all of the fields of space is what I call absolute motion, but which is you could also call pure energy, but incredibly energetic fields leading toward what you could say is pure energy without defining it here. Um, but anyway, the leading from these energetic fields upward towards the more entropic or still or slow or, less energetic levels. And so subatomic particles would be defined by the field where they are located within this multi-dimensional block universe. So say, for instance, we have a nucleon here, we have maybe a quark here, we have maybe a Higgs boson here, and we have maybe a string or something here, depending. Maybe some quantum foam, vacuum energy. And here, as in quantum field theory, particles are excitations of fields, but those excitations have the nature of being holes within the fields where they're located. And the nature of the particle is determined by where its horizon, the horizon of its hole, is located in this multi-dimensional block universe, the fields of this multi-dimensional block universe. And the difference here is that we understand these fields lie alongside each other in order. It's not like we have a single, let's do a new layer. It's not like we have a single dimension of space, which is how we understand it now, where all these fields are located with different particles having their own field, but they're all sort of bunched together in one spatial reality of our universe. So this is like the main issue that physics has with truly understanding the nature of subatomic particles and singularities, as we'll get into probably, is that we're looking at it all from a flat perspective, and everything's like bunched together, right? So you can say all these fields, these discrete different fields, exist within our universe, within 3D space, but in the end, it's just a jumbled picture because these particles all have different properties and qualities, and some are smaller than others, or how we understand it, smaller and bigger. But again, it's just a jumbled picture because we don't have the clarity to understand that they actually exist within different dimensional fields, moving into the realm of the very small, which is in this fourth spatial dimension or direction. So this idea of the fourth dimension lying in the direction of the very small is vital to actually understanding what we're observing. So say, for an instance, let's get into something maybe we haven't covered a lot. So say, for an instance, we are looking for a Higgs boson, so the God particle. So when we create a super collider, this is going to be a little odd to people who aren't grasping this idea of fields lying alongside each other, extending into what we think of as the direction of small. But what we're doing with these super energies that we create, we're actually digging a hole in our universe that penetrates deeper fields. So in that sense, when we create a particle, it creates and decays, we are actually creating it by poking this hole in a field. See, wave-particle duality is such that there's this field of energetic waves or whatever. It's an energized field. And we say that when observed, it collapses into a particle, but actually the observation is like poking a hole. The observation itself, the energy of the observation is poking a hole. So that hole is the particle, and then it can decay or, swallow itself up. And so when we create more and more energies, we are actually digging deeper into the fundamental fields of the multi-dimensional block universe, into more energetic fields. And we're getting down to where vacuum or zero-point energy is. So that also explains, if we pull up another layer, that explains how vacuum energy can be there, and the math can say that it should be incredibly great, but we don't observe that, is because it's not, here's our 3D universe. This is us. I'm going to draw a little picture of one of us. It's not me, because I don't know. I don't want to look like this. Somebody else can. And then there's a little star, a galaxy. So it's not like there's these incredibly vast energies right here, and we're going like, why don't we observe them? They're in our space somewhere. Maybe they're curled up into tiny, tiny little curls. No, they exist in the fourth dimension. So there's these vast energies underlying our universe, and they can so-called pop into being, 0 point or vacuum energy, or the particles, virtual particles, is that what they're called? 0 point particles, vacuum particles, vacuum energy, that we say it is constantly popping into being and disappearing. But now you can see how it's like if there's an ocean, a turbulent ocean under a calmer field, and it's bumping up against it, and then these energetic drops are like exploding here and then just falling away. That's why there can be an underlying 0 point field or vacuum energy field that's incredibly energetic, possibly even reaching the point of infinite energy, and that it's not here in our 3D space. See, the understanding that the realm of the very small is a fourth spatial direction describing a fourth spatial dimension to the universe, which is part of a multi-dimensional block universe, or what I call superspace. That explains how something like this can be. And another thing it explains that I've gone into a bit more, so I probably won't go into this in too much depth, is the singularity, and that includes the singularity in terms of Big Bang and black holes. So when we talk about a black hole, so there's this hole, right? And you've actually seen pictures like this. There's a black hole, maybe the event horizon or something. So we're actually drawing it out, but we're just not understanding that this is literally a hole moving into deeper dimensions. And as it gets smaller and smaller and smaller, it's going inward in this fourth dimensional direction, right? So when we say it reaches a point of infinite density, the reason we say a point is because we think it has to be small. So it's a point, right? Like a point particle. But if it's a field, if it's fields lying alongside fields and this direction is going in a direction, then it's just infinite, right? It's not a point. The math does not say it's a point. It just says it's infinity, because it's a direction. So when we move, when we allow the math to tell us that gravity curves inward and keeps curving, right? We don't stop it. There's nothing to stop it. We allow the math to say that it keeps curving, it automatically reaches infinity. Because it's not a point. There's no infinitely dense point. It's a direction. Direction. I'm not going to write this out, but we're going to go D-I-R. It's a direction. The fourth spatial direction. So that can tell us about the infinities, that the infinities are a direction rather than a point. And so whether you're talking about a big the Big Bang or a black hole, it's the same thing. It's a direction. So, for instance, the Big Bang, we again, because of the concept of the Big Bang, which is a concept, we allow the math to curve inward, continue curving inward into infinity. So what that is telling us, and I just fucked this up, sorry for the language. What that is telling us is that the curvature of gravity is curving into infinity, right? Gravity curves into infinity. Now, that can be stopped, right? It doesn't, we don't, I mean, there could be an object here, or we could just stop the math with a renormalization or the Planck length or whatever we decide to do and not go on into infinity. But what the math is saying, if you allow it to keep curving, gravity, the curvature curves into infinity. Okay, so that's what the math is actually saying, is that the curvature, which is gravity but actually holes in fields of space, moves into infinity. Okay, so that also the Big Bang, when we think of the Big Bang where we have an infinity, we're also talking about layers. Now these layers didn't exist at the time, but we're talking about this massive energy moving upward through fields, perhaps creating the fields as it moves upward or forward. And so this would be the infinity, would be a field in this direction that goes into infinity, right? And so let's actually change this up and actually draw the fields out. So say let's just say there's infinite energy here, and there's an incredibly energetic field. This would be like the cyclic universe model. So then the energized field might, like quantum foam or something, bump the field next to it, or the potential field, whether it's already manifest or not, and boom, right? You have a Big Bang, right? The energy, and this is what the cyclic universe model people have suggested, something like this. They're just not looking at it as moving into the realm of the very small, right? So this goes from macro to micro. So that's what's missing in the cyclic universe model, but it's a similar thing where, one brain, or I use the term field because of quantum field theory, but people have used the term brain, bumps another brain, and that's the Big Bang. Well, imagine if that keeps going, right? And it bumps another brain, and it bumps another brain, and it bumps another brain, and this is going from the energetic to the entropic, right? So that's the Big Bang, right? That's the Big Bang, and then that's the progression of energy through fields of space, moving from the micro to the macro, moving from the energetic to the entropic, and until we reach our universe, and here's someone. That's not me. It's a very strangely proportioned individual, I will have to say that much. And then there's a galaxy. So, so the Big Bang theory is describing this in time, but it's also just a progression of the fields of space now. When we observe these vast energies inward, that's here now. So all of that, let's just close all of this out for now. All of that is talking about how the understanding of the fourth dimension and these fields of space lying alongside ours can just put an entirely new context to all of these different things, including time. So one of the things I talk about, which again I'll just touch on briefly, is that time is the motion of energy through this block universe, or the motion of the block universe. So what I say is time is not a fourth dimension, it's motion through the fourth dimension. And so I'll quickly pull up one of my little pictures here, but we won't go into this very deeply here. But what I talk about is how, this block universe, so here's our universe and here's the deeper fields, and there's this motion, and that motion is time. So that motion is time, the flow of time. It's an actual physical motion rather than it being some sort of mysterious thing where it might go forward or backwards. Mathematically it doesn't have to have direction, but we know it has direction. But it's an actual physical flow through the greater block universe, the multi-dimensional block universe. And let me just pull this up again real quick. And I hear a train, which is odd because there's no train around here. Okay. So, yeah, time would be, so say you have our universe, you have deeper fields, underlying energy. This is a greater multidimensional block universe, of which our universe is one 3D field, and time would be this motion. You could look at it as motion of energy through fields. You could look at it as the motion of the block universe itself, or as fields themselves. Either way, it's this motion in this fundamentally different direction, right? And so that is what time is. It's also related to gravity, because this motion of fields in this fourth direction means that the holes that curve our field of space, if this field is going, let's say, up, then an object traveling in the linear direction in the field of space will be sort of swallowed as the horizon of the hole moves up over it. So I get into that more. By the way, one quick thing I want to say about this picture of the block universe is that I only create these edges for the ease of explanation, but actually a field could be hypothetically infinite in extent, right? So these fields could all be hypothetically infinite in extent. They don't have to have a boundary, but I just, again, have a boundary. So just as our universe could hypothetically be infinite, but then of course there's this fourth dimensional direction, which is also hypothetically can move infinitely in that direction. So I've sort of covered in a more rambling way some of the core ideas of superspace theory. So I just want to talk about a little bit, talk a bit about my own process for coming up with this, because I haven't really talked about that. So I kind of got, it was sort of a revelation that just came to me suddenly. And I had studied physics at a layperson's level since I was in my early teens, just reading popular books like A Brief History of Time. And in, I think it was 97, I was just thinking about the curvature of space and time, right? And so like, well, let's do it this way. Let's make this bigger. So a field of space and a ball in a field of space. And the idea of a ball going inward into the very small being like a tunnel occurred to me. So if you look at this picture right here, this can be a ball with smaller and smaller layers, or it can be a tunnel going inward or going that way, away from us, right? It can be a tunnel. So it hit me that moving inward is like going into a tunnel. And it just occurred to me, and the words that came into my head were a ball is a wall, meaning it's a solid object sort of like surrounding or blocking what's actually a tunnel curving in a fundamentally different direction. And it just hit me. And I realized that's when it hit me that it really is like a tunnel. It's just curving into this fundamentally different direction. And it just hit me that when we get inward to those fundamentally different levels of physics, we're no longer smaller. It's a fundamentally different dimensional direction. And that, honestly, was in '97, and I've tried to articulate it to myself many times and always expected someone else to come up and say, well, size equals distance when you get in far enough, and that at the very fundamentally small realms of subatomic physics, things are not smaller. But no one has. No one's had that insight yet. But the math is telling us that. I read something recently, and I don't know if I could find it online, but it said how if you're if you are looking at the math, then when we go back toward the Big Bang, you can look at it that space is not getting smaller, it's getting larger. I mean, someone was just looking at the math. They were not saying this was actually the physical case, as I'm saying, but they're just suggesting the weirdness of it. The same way when, they're saying that the universe could be inside of a black hole, right? Could Earth be inside a black hole? Could the universe be a black hole? Could it be inside? These are new uh, these are new ideas which are stemming from the fact that when we just analyze the math, it's not talking about size. Expanding into it, okay, but that's not. But it's not. The math is not talking about size. So if people they're not getting it yet, that literally when we move inward to fundamentally different levels, it is not size anymore, it's distance. So that's the truth. People are getting that from the math without understanding the full connotation of it. So, are we living inside of a black hole? Okay. Part of an immense array of separate universes, each orb in the two I said. Do we live inside a black hole? It's for humans to live. There's now see that's I can't find. Okay, that may be it. Are we living? Oh, that's the one I just had. Baby universe that looks like a black hole to outsiders. Anyway, these are ideas such as space getting bigger as it moves inward, or as it moves backward in time toward the Big Bang, and things like this are ways in which we're starting to understand that the math is not necessarily saying that the realms of the very small are small. And that's, I think, what we have to understand is that mathematically speaking, things like when we move in the direction of the smallest things, math says nothing about them being smaller anymore. And I'm not talking about, real quick, I'm not talking about in our own macro space, right? So like physicists do distinguish between micro and macro space. rightfully so. And in macro space, I go into this in my book, there are things that are bigger and smaller. So here's a funny little picture I created where, and actually I'll just go ahead and pull it up on GIMP here before I sort of conclude this in a little bit. But so what I'm showing here is that here we're in our universe, and I'll do blue lines since I don't want to change it to black, and also it stands out, right? So here we are in our space, and you know the elephant is bigger than this little guy, although this guy's pretty big. Like, look at him and the elephant. And then the mouse is smaller. These are bigger and smaller, right? And if you had like a bug here, crawling, and then you had like a mountain here, it's in the distance, but the mountain is bigger than the elephant's bigger than this little person. Let's make him happy. And the mouse is even smaller, although it's probably a rat if it's that big compared to an elephant. Anyway, so these are bigger and smaller. It's when we reach fundamentally smaller levels, right, that we start to go into this fourth dimensional direction. So I think, and I go into this in other ways where I talk about how if we were in a sheet of glass, and we could see objects in other sheets but could not touch them because they weren't actually in our sheet. So here in this one, I talk about, because one of the things I go into in my book, Superspace Theory, is that there is interaction. So when I show all these fields, and let's just actually bring up a layer, when I show all these fields, it's not like these are completely separate, right? So here's us, weird little mutants, and here's some nucleons, some gluons and pooons, or whatever they're called these days. And so it's not like there's no observation, because like with our tools of electronic microscopes, we do observe deeper dimensions, right? So it's not like there's no connection or no observation. However, we can't necessarily interact with it in a way that, if things that are macro here in our 3D space, we react with, directly. So what I was saying, if you lived in a sheet of glass, let's bring this, a flat sheet of glass, and there was another sheet beside our sheet, and there was a moon there, and that moon reflected in the glass and looked exactly like it was in this glass, we would be surprised because we couldn't touch it. We'd be like, what is this? I'm not able to touch it, right? So because we were flat, moving this way and that way, but unable to move this way outside of our glass, all of our understanding and analysis would be about this as something, immaterial or whatever. But then I get into how if we had a tool like a gun that we could shoot bullets that curved out and actually did affect this, we wouldn't understand it as curving out. We'd just probably see it as like tiny bullets affecting, let's say the moon reflects as something super tiny, right? And our gun shooting. We just understand it as all existing in this sheet of glass, right? The gun shoots tiny things at these tiny dots and bounce off. We would not understand that this is actually curving out of our flat dimension into a deeper dimension. But that's what's happening with our, super powerful microscopes or things like the Large Hadron Collider that are actually, you know, tearing into deeper fields of space. So all of that is essentially to say that until we realize there are fields of space lying alongside our three-dimensional space, and that this is the direction that we think of as small, and that at fundamentally smaller levels of physics, we're not getting small anymore. We're moving in a fourth spatial dimension direction of the fourth spatial dimension. Until we get this, then we're always going to have a muddled sort of bunched together picture of physics, which will, there'll be certain questions we will be unable to answer. So those are some reflections on superspace theory with a little bit more conversational style and personal reflection. I hope you enjoyed it. Thank you for watching.